Now, when we create a complete theory of space-time based on differential geometry, we're going to come up with all kinds of geometrical quantities, and we're going to get a more complete theory than just this Newtonian thing reinterpreted as curved space-time. We're going to get a theory which has all those gammas, right? All those gammas are going to come in. Now what happens is, when you create that theory, it's very beautiful and very complex. When you stick in the parameters of, let's say, the situation of radial infall, you're falling in to a planet-sized object rather than a black hole or something like that, right? Everything collapses out and cancels out and goes down to zero, or it gets so small that we couldn't possibly measure it, and there's only one term left, and that's the gamma, that's gm over r squared. Close to the sun, like where Mercury is, the gravitational field is strong enough that another gamma crawls in, and we'll see that another time. And that's why there's this famous precession of the perihelion, which was noticed even by Newton and so on. They didn't think that it was a problem to theory, they just thought maybe there's another planet, they didn't know exactly what it was. But the bottom line is that in the full theory, you have some kind of geometrical structure which, in certain very simple cases, like when gravity is weak, like far enough away from the sun where we are, right? And to the precision that we can measure things, it looks like there's only one gamma, and that's exactly the gamma that's provided by Newton's theory. So we can't really say that this gamma is the curvature of space. This gamma is the connection curvature of the world line. It corresponds, it's the shadow of some more sophisticated thing, or sum of things, which collapses down and becomes simple and projects down. It's the shadow of this more complicated thing, which is the geodesic curvature of a real four-dimensional space-time in a full rigorous theory. I'm going to label that from now on gamma, let's say not RT, but RTT. Again, I'm not going to get into right now why two T's and this, but basically this is going to be the real quantity in curved space-time, the thing that enters into the geodesic equation that we saw, right? And its shadow, so to speak, is the thing that we've been talking about all this time, which is the world line connection curvature. Now, naively, we're going to expect that one is equal to the other. Why? Let's say, what would you say is a good reason to expect that, or why would you say it's really wrong to expect that? How would you conduct that argument? Anybody?
Sorry, can you try the question again one more time?
Sure. I'm claiming that this shadow quantity, this world line curvature, which is a purely flat space-time quantity, it's Newton's equation, A equals gm over r squared, right? Which is also obviously just the curvature of the world line. I didn't need to get anything sophisticated to call it curvature of the world line, just using calculus, right? It's not really space-time and curvature, it's just a diagram. Is it appropriate to expect that really that gm over r squared will also pop out in the full theory?
Well, yeah, because Newton works really well in a lot of
Exactly.
situations.
Exactly. So that comes to the heart of sometimes when people talk about, well, Newton's theory is wrong, Einstein's theory is correct. Einstein proved that Newton's theory is wrong. And physicists discuss these things, or philosophers of physics. What does it mean that a theory is right? What does a theory is wrong? I mean, we know that Einstein's theory is wrong because obviously we need a quantum gravity, and maybe there'll be something after that, etc. So we just get progressively closer to a correct theory, if there is such a thing. Maybe there's no end. Maybe it's an infinite progression, and there's nothing at the end. We just get clever and clever, right? So that's really philosophy. We don't really need to deal with that. We have a theory as good as we can get, and Newton's theory is good. It's correct. For what it is, it's correct, and it works extremely well. You can predict the eclipses, I don't know how many years ahead, right? I think they probably even did, I don't know if they used any corrections from Einstein's theory in launching the first, let's say, satellites and so on, orbit around the Earth, actually, human satellites, the astronauts. I'm not sure if they did or not. So it works very, very well. So obviously, when we use the full theory, it's kind of like overqualified. If we use the full theory to figure out, with what speed does this fall, or with what speed does it hit the ground, it's kind of overkill. Because we can get a precise answer to within, let's say, our measurement ability, let's say, right? So clearly, if we use the full theory, we should get that same answer with maybe a tiny correction that we can't even measure the difference to, right? The only question will be, will it come out gm over r squared? Will it come out something strange that gives you the same number? Now, I'm not sure whether that can even happen. I mean, I don't want to get into that kind of discussion. Can it be that you'll get something entirely different that somehow gives you the same answer consistently? I'm not sure, okay? Let's just assume that it can't, and therefore it has to be that gm over r squared will appear there somewhere, okay? So we're going to naively expect that in the appropriate situation, in other words, outside a sphere roughly the mass of the Earth, you drop something, whatever, this is the connection. Or outside a sphere like the sun, roughly this distance away, or whatever Newtonian stuff works, we're going to expect that the full theory will give rise to basically the same thing, and we'll, in a later lecture, we'll be able to see exactly how it comes about. Okay, and that's very, very exciting. That's really one of the main things that gave great joy to Einstein when he plugged in the numbers and he came up with exactly the correct prediction for example, the perihelion of Mercury. Because his theory was able to explain some little tiny anomaly that was known for hundreds of years. Not that he was therefore able then to, change anything, but it was clear that this little tiny prediction, right, this little tiny correction factor comes out so naturally in that theory and comes out precisely to be what everybody was wondering about, okay? But other than that, we get the same thing.